Hey folks, how y'all doing? Good to see you guys today. So we're getting ready to start our second chapter here. So we're going to be looking at limits one more time as they get us into our next little piece for calculus. That would be definition of a derivative. All right, so first up, just remember kind of where we're going here. Calculus, we said, first of all, is based off limits. And then from there, we said it was founded on two famous problems. One of which was what we call the tangent line problem. So just as a quick little brief reminder, say we had ourselves some sort of 2 points on a graph. Now, if I wanted to know the slope of these two lines, we're going to move that. There we go. Oh, that's not what I want. There we are. If I want to know the slope of these two lines, we said we were going to end up using the formula y2 minus y1 over x2 minus x1. But we also did something else. And let's see if you guys are kind of quick little recall here. We said, what if we let this be x? And then that would make this f of x. And what we said we were going to do is, what if we allowed this right here to be x plus delta x? And the reason why we're using delta x is we said delta x, that would be the distance between these two values. And if that was x plus delta x, then that meant that this y value here was really f of x plus delta x. So if we were to go and find the slope of that line, so essentially we're doing a little slope triangle here, and we're trying to figure out the slope of this line. And we remember that slope is rise over run. That means slope would be the difference in the y's minus, or divided by, sorry about that, difference in the y's divided by the difference of the x's. So x plus delta x minus x. So we had our first point, and then we're subtracting that second point. And if we were to do that, so here's our point 1 right here, and this is point 2 down here. I lied, point 2. There. That's our second point, is our first point. So y2 minus y1 over x2 minus x1. And if we cleaned that up, we end up getting ourselves this thing that we called the difference quotient. And this difference quotient is really a way for us to find the slope between any 2 points on any curve. So another name for slope is rate of change. So what we end up getting here is that slope is really nothing more than average rate of change. And then we get to our tangent line problem. Now, on that tangent line problem, we took that idea and we said, okay, well, what if we wanted to find the slope when that difference between those 2 points between those two x values is 0. Well, when that happens, we end up with something kind of like this. We're going to keep letting those points get, 2 points get closer and closer and closer until we end up with something where the distance between the 2 points is 0. In other words, it's at a single point. Well, we went through and we said, well, this is the idea. We called this idea a derivative. That is instantaneous. Instantaneous rate of change. You ever have those words that are just hard for you to spell no matter what? I do. Like this instantaneous. For whatever reason, I always struggle with that. So we use this idea of a derivative. Now, derivatives can take on a whole bunch of different little symbols. We oftentimes when we refer to a derivative, we don't want to write it all the way out. So we have different symbols for it. Our first symbol is an apostrophe x. So f apostrophe x. And this one is read as f prime. So the apostrophe is the word prime. F prime of x. So it's not f apostrophe x, it's f prime of x. And so we can use that symbol here to represent this difference quotient. When the difference between the two values is 0, well, that's a derivative. That's instantaneous rate of change. Another one you'll see a lot is this, dy over dx. And what this says is the phrase change of y change in y with respect to x, or the difference in y with respect to x. Should probably just type that out, but whatever. So there's technically 4 different symbols for derivative, but a majority of the time, they both always come down to this idea of a fraction, dy over dx, change in y with respect to x, or this apostrophe, which means prime. So what this allows us to do is it allows us to develop some sort of expression for us to be able to determine the derivative or the instantaneous rate of change, the slope at a particular point on the graph. We don't need to have 2 points to deal with the average rate of change. We need 1 point to deal with the instantaneous rate of change. And this, friends, this is what a derivative essentially is. Yeah. So let me show you what we're going to do today. We're going to go through a bunch of different things here. So the first thing, we're going to determine the derivative of f of x. After that, we are going to evaluate the derivative at a given x equals c value. We're going to determine the equation of the tangent line when x equals c. And the last thing we're going to do, we're going to do something called use the tangent line to find the what we call linear approximation for an x value that is really, really close to c. All right, so first up, what the heck does all this mean? Let me show you. First thing we need a function. We're going to use f of x equals negative x squared plus 7x. Oopsies. So this is what we're going to end up doing. So just so we remember, let me go ahead and write in the definition of a derivative so we know what that is. So essentially, we're going to come up with a function that's going to allow us to determine the rate of change at any instant on a curve. So that means the derivative here, delta x, and so as delta x approaches 0, and that's going to be f of x plus delta x. So we're going to use this definition to help us out. Now, quick little side note here. This is just me, just my own little 2 cents. I don't like using delta x a lot of the time just because in my mind, that's really, really close to x in general. So I like to usually specify it. So if you guys are all right, I'm going to actually make this. I usually use a different variable. A lot of times I'll use the variable h. So I like to say a lot of times let delta x equals h. So any place I see a delta x, I'm going to use h. And the reason why I do that, again, it helps me just clarify what's x, what's delta x, right? What's x, and in this case, what's h. So I'm going to find the derivative of this function. So I want to find this another function that will allow me to find that instantaneous rate of change. So instead of using delta x, I'm going to use h. And by the way, quick side note, we always want to make sure that it's 0 over 0, but if I plug 0 in here, anytime you use a difference quotient, it's always 0 over 0. So I'm going to just skip over that portion today. So any place I see an x, I'm going to plug in x plus h, or x plus delta x. And then I'm going to subtract f of x. I'm going to put it all over h. So in that first function, every place I see an x, I'm going to plug in x plus h, or x plus delta x, if you're still using delta x. Again, it's just easier for me to clarify. All right, so now we're going to go ahead and simplify this all the way out. So I need for myself to have some sort of expression. And again, like we saw in the homework in chapter 1 when we did a couple of these, if we do this right, anything that does not have an h in it or a delta x in it will go away. So when I multiply this all the way out, negative x squared minus 2xh minus h squared plus 7x plus 7h plus x squared minus 7x. And again, you guys can go through and do all the multiplication yourselves. And by crossing out some like terms here, I end up with f prime. Oopsies, you didn't do that. I end up with something that looks kind of like this. The x squareds go away. I still have the negative 2xh minus h squared. 7x's go away, and then I have plus 7h. I'm going to divide the whole thing by h. So notice, the x's all go away. So x squared went away here, and the 7x went away here. So if I do this right, anything that does not have an h, or anything that does not have a delta x, will go away. So f prime of x is going to be equal to the limit as h approaches 0, and I get negative 2x h's cancel out, so minus h plus 7. And when I plug my 0 in there, I end up with negative 2x plus 7. In other words, this expression, f prime of x, the derivative, the function that allows me to find the instantaneous rate of change at any x value would be negative 2x plus 7. So now, quick little timeout here. Just so we're kind of aware of what's going on here. If I were to take a look at this function, and again, it's a parabola, it's open upside down. I'm hoping you all can see that. All right, it's got x-intercepts at 0 and 7. So what I'm basically saying is here is when x is 2, what I'm trying to do here is I'm trying to figure out the slope of the tangent line at that value. The slope of the tangent line at that value when x is 2. Well, I can see that it's going to go up. So part 1 said find the derivative, okay? Determine the derivative. We did that. This is the derivative. This is part 1. Part 2 said evaluate the derivative when x equals c. Well, if we look at our tangent line here at x equals 2, it's going up. It's an increasing line. So I'm going to expect that when I plug my tangent line in here, I'll use a different color, so part 2. When I plug 2 in for this, I should be getting a slope that is a positive number because derivatives are slope at a single point. It's the instantaneous rate of change. Average rate of change, slope, instantaneous rate of change, derivative. So at that single point, that tangent line would have a slope of 3. In other words, the instantaneous rate of change at that value x equals 2 would be 3. The next part said determine the equation of the tangent line. Now, for our purposes here in pre-calc or in calculus, we are always going to use the tangent line in point slope form. The point slope form never makes us ever simplify anything. We're just going to leave it in this form. So, friends, I know what x is, it's 2. I know what my slope is, it's 3. I don't know what my y1 is, my y value. Well, to get my y value, just go back to the original equation. I need to know what that value would be. So I'm going to go back to the original equation, just going to plug 2 in here. And that would be negative 2 squared plus 7 times 2. So we plug everything in here. I just realized I graphed my line wrong. No, I did it right. All right, so if we plug this in here, when x is 2, I had a little brain fart there for a second. It happens. I get negative 4 plus 14. So that would be f of 2 equals 10. So now I have my y value, 10. I have my x value, 2. I have my slope of 3. I'm going to write the equation of the tangent line. So y minus y sub 1 equals 3 times x minus 2. Now the last part's going to ask that I do a linear approximation. And here's what I mean by a linear approximation. Notice, if I were to zoom in real close up to this point, the tangent line, the equation of the tangent line would be very close. The y values would be very close to the y values of my original function. So when they ask for a linear approximation, what they're really asking for is don't plug a value in for an equation, into the original equation, what they're asking you to do is they're saying, hey, if we're going to find the linear approximation of a value that's really close to 2, you can plug it into your tangent line to get a value that's really close to 2. So by moving the 10 over, I get an equation of a, here's the other way to write my equation of my tangent line. I can use that to find the linear approximation of values really close to 2. So for instance, what if I were to say, estimate f of, let's try 2.1 using a linear approximation. In other words, it says, all right, so I know that this line right here is really close. My tangent line is really close to my curve at any x value really close to 2. So what if we wanted to find out the value when it is really close to 2? So 2.1, that's pretty darn close to 2. This is not an exact value. This is an approximate. And by the way, because it's an approximate, you need to realize you will not get the right answer if you put an equal sign here. It must be an approximate sign. This is an approximate value. So we're going to use our tangent line to approximate that value when x is 2.1. Now, we have graphing calculators, and if I wanted the exact value, I'd plug 2.1 into my original equation and I'd solve it. But on the non-calculator portion of the test, or sometimes we just get really ugly functions, it doesn't do us much good to plug things into our calculators, well, especially if we don't have one. And so we can use this value plus, which would be equal to 10.3. So that means if I were to plug 2.1 in to my function, it would be really close to 10.3. You know, if you plug it in, let me grab my graphing calculator here real quick. What would that value be? And I plug it in here. The actual value itself, just to show you what it is here, the actual value itself, if I were to plug it in, it would be 10.29. Well, 10.3 is really close to 10.29. So that linear approximation says get really, really close to it, but you're not going to be able to find it. So here's what I want you guys to do. I would like you guys to go through and do the same thing, but this time your function is going to be this. F of x equals the square root of x plus 3. And then I want you to go through and do all the same stuff, but I'd like for you to try it using an x value equal to 1. So you're going to find the derivative, evaluate the derivative, get your tangent line, and then do a linear approximation. So your linear approximation is going to be f of, let's go with, let's try 1.1, I think. 1.1. So your function is root x plus 3. X equals 1 to get your derivative and tangent line. Then I want you to use that tangent line to approximate it when x is 1.1. All right, go for it. Let you guys pause the video, see what you come up with. All right, you guys are probably getting close to being done here. I'm just erasing and having a wonderful time doing it. So you guys are probably just watching me erase. So I'm just going to apologize now. Today is one of the longer ones we do on the course of the year. All right, so I'm going to start off my let statement again. Let delta x equal h. So just because I don't want to be dealing with it, I'm going to go and figure out my derivative then as h approaches 0. So f of x plus h, so root x plus h plus 3. And then I'm going to subtract x plus 3 all over h. And we've already shown that it was 0 over 0 to begin with. So if you notice, this is really honestly just one of our rationalizing problems. So I'm going to multiply everything by the conjugate of the numerator. We do multiply the top by that, and we're going to multiply the bottom by that. So plug it in, f prime of x, whoop. And we clean stuff up a little bit here. By the way, friends, today, last day that we're dealing with limits. All right, check this out. We might be figuring out some things along the way here. And when I do my difference of squares, I end up with this square root canceling out. And I'm going to subtract the second square root canceling out all over and when we distribute it, notice x's cancel out, my 3's cancel out, and then not just that, but notice my h's are going to be canceled out because they're going to divide into each other. That's all I'm going to have left. I'm going to be ending up with the limit of 1 over root x plus h plus 3 plus I'm sure you guys probably saw that little typo there, plus x plus 3. And when I plug 0 in for h, I'm left with 1 over 2 root x plus 3. Friends, there's my derivative. So this expression, this equation right here, will allow me to be able to find the slope at any point on this curve. I'm able to find the instantaneous rate of change at any point on this curve. So second part, we're dealing this when x is 1, so we're going to plug 1 in here. F prime of 1. So the derivative when x is 1 would be 2 times the square root of 1 plus 3. That whole thing is 1/4. So that means the instantaneous rate of change when x is 1, at that point is 1. Well, if I'm going to write the tangent line, I need to figure out what f of 1 is. Now we're on part C here. We plug it back into the original function, 1 plus 3, and I end up with 2. So that means my tangent line, the equation of my line tangent at x equals 1 is y minus 2 equals 1/4 x minus 1. And then I asked you guys to figure out what is the linear approximation of 1.1. So if I plug 1.1 in there, that would be about 1/4 times 1.1 minus 1 plus 2. So 1.1 minus 1 is 0.1, which would be 1/10. So I have 1/40. Let me show that. 1/4 times 1/10 plus 2, which would be 2 and 1/40. I get a number really close to when x is 1.1. Well, friends, let's try this one more time. I really want to make sure we really hammer this in. I want you guys to have an idea about it. I want you to feel good about it. So what if I give you an equation like, oh, how about 1 over x plus 2? And let's do this when x is -3. And from there, I want you to figure out the approximate of -3.1. Let's try that. All right, friends, go for it. Go and pause the video, or while you're doing that, I'm going to go and erase the dumb thing. I'm much quicker at erasing this time. That was some mad erasing skills right there, friends. All right. You guys have probably unpaused it. Here we go. I'm going to plug my h value in here. So 1. Notice all our little ways to evaluate limits analytically. Notice how they're all showing up here. Go figure. I mean, there was a reason why we learned everything we did. Huh. Did not see that one coming. All right, well, if I'm looking at this here, I notice that I am going to have a big, ugly common denominator problem. So I got to multiply every single thing by the common denominator. And that common denominator is going to be x plus h plus 2 and x plus 2. So everything is going to get multiplied by that. Gotta be careful. I'm going to go off the screen here in a second. Zoom would not be happy with that. Ah, sloppy. All over. Everybody gets multiplied. All right, so when we do that now, cross off the things that go away, so gone. And let's see here. This is going to go away, gone. And I'm left with h approaches 0. I have x plus 2 minus x plus h plus 2 all over h times x plus h plus 2 and x plus 2. So these limits allow us to be able to figure out instantaneous rates of change. So what, by the way, what cancels here? We have the x's that cancel out. And again, if we did it right, everything that has besides an h will cancel out. So now I'm left with, I'm going to write this one more time because I want you to see what happened here to this. I'll need to write that. Because if we're not careful on this one, we're going to lose a sign. Notice how there's a negative out here, right? So I mean, makes this a negative h all over h times x plus h plus 2 and x plus 2. Well, the h's are going to go away there, and I'm going to be left with just a -1 up top. So h approaches 0. We have a -1 up top, whoop, all over x plus h plus 2. And x plus 2. And if we plug our 0 in there, we end up with -1 over x plus 2 squared. So there's our derivative. It's going to allow us to be able to figure out the slope of any point. Alrighty, friends. So once we have that, now we're able to go ahead and evaluate our derivative. I'm going to go through fairly quickly on this one because, again, it's just plug and chug. So if I wanted to figure out the derivative at -3, I plug it in there, I get -1 over 1, which is -1. So my derivative would be -1. If I plug in if I want to figure out the tangent line, I'm going to plug in -3 in for my x value. So I get 1 over -3 plus 2, which would also be -1. So that means my tangent line is going to be y plus 1 equals -1 times x plus 3. And last and certainly least, we're going to evaluate this. We're going to use this to evaluate, do the linear approximation for -3.1. So there we are. -1 times, and again, notice how I use the approximate symbol for that. And again, it only approximates values that are really, really, really close. Can't be used, say it couldn't be used for like when x equals 5. Couldn't do that. Yeah, I mean, I guess it could, but the approximation would be so ridiculously far away that it would do you no good. So let's see here. F of -3.1 would be about, oh, that's -1/10 times -1, that'd be +1/10 minus 1, which would be negative 9/10. Again, pretty close. Well, there is another form to be able to do this. That definition of a derivative gives us a formula So the limit definition gives us a formula for finding any derivative. But there's another form that allows us to be able to find the derivative value at a single point. Now, if you have to use a derivative to find more than one derivative value, use the definition. But if you have to ever find the value of just one derivative for a function, a lot of times it's better to use the alternative definition because it will actually crank out the value for you. It won't give you an expression that you plug x values in to find the derivative. What it does, so we're going to do this for some x equals a value. Let's do this. X. We're going to do it at some x equals a value, some random number, x equals a. So this definition, what it does is it says, all right, you can find the value, that specific value at that derivative by using this one, f of x. It's going to give me a specific number that pops up. It is not going to give me an expression. If I have to take some given function and I have to find more than one derivative for it, I'm not going to use this. So for instance, say I give you something like this. Determine the value of f prime of x when x equals, let's try -3, for f of x equals x squared plus 2x. In other words, if I'm just going to do one derivative value, notice I just x equals -3. If I also said x equals -3 and x equals 2, I would use a definition of a derivative because I'm going to do it more than once. But if I'm doing just one value, of a derivative, this alternative form really works out pretty cool. So I'm just going to do it once for you just so you can see what it is. All right. So my a value here is -3. Okay? So that means in this problem, a is -3. So I need to know what f of a is. So I'm going to plug -3 in. So I have -3 squared plus 2 times the -3. And when I plug that in there, friends, I'm going to get 9 minus 6, which is 3. So here's how this little formula works. It says, all right, I want to figure out the derivative at -3. That means I'm going to plug in -3 in for a, which we've already done. So our first part is the f of x part. Okay. So my f of x is x squared plus 2x. And I'm going to subtract it by my a value. My a value, or my f of a value, well, that was this 3 value right here. So I'm going to plug in positive 3. All over x. That's a weird looking x, friends. X minus my a value. So I got to go figure out my a value is. That's this one. So we're going to plug that in. So if I plug negative 3 into my problem here, if I plug it straight into this problem, I'm going to end up with negative, oh, I lied. You have 3 minus 3 all over negative 3 plus 3, which is 0 over 0. So it is indeterminate. So I'm going to go ahead and go back and use my rules of indeterminacy, or if it's indeterminate, it means I can rewrite it. So let's see what we can rewrite it as. I have x squared plus 2x minus 3 all over x plus 3. I can rewrite it as, in factored form here, x plus 3, x minus 1. And all of a sudden you start to see where that removable point of discontinuity is, that hole is. So the x plus 3s are going to cancel each other out. And hopefully you kind of see where this is going here. It's not going to leave me with an expression that I can use over and over again. It's going to only end up with a numerical value. So the derivative is going to end up being negative 4. So the derivative of negative 3 would be equal to negative 4. And if I only have to find the derivative of just one x value for this function, I could use this alternative definition. It's quicker. It gives me the value quicker. But if I have to do it for more than one value, don't do it. Use the definition of a derivative, because you don't want to have to keep repeating the same work over and over again. Might as well just do one limit and then get a value, an expression you can plug stuff into, rather than having to do 2 full limits. So that's the alternative form of a derivative. And again, I'm not going to necessarily give you another one here. I mean, I guess I can. I'm not going to necessarily do the problem. I'll give you the equation. What if I told you f of x equals, oh, I don't know, let's make it negative x squared. I'm just going to give you the value for the answer. All right. And if you guys want to see a little bit more on how to do it, go ahead and let me know. So pause the video if you want to try it and see what you guys come up with. All right, you guys ready to try it? Okay, so if I were to plug this in, if I were to go through and do it, hopefully you came up with the answer of 5. Or if you did it right, you should have came up with an answer of 5. Okay. Again, if you want a little more help on this, we can look at it tomorrow in class. However, we care more about the definition of a derivative, friends, not necessarily the alternative form of a derivative. All right, so here you go. This brings us to kind of a big theorem. The theorem says this: if a function is differentiable, that means you can take the derivative, differentiable at a point at a value, that's what we should say, x equals c, then the function is continuous at x equals c. And the phrase you'll hear people use time and time and time and time again is this: differentiability implies continuity. You will get a ton of points on your AP test on the free response portion if you remember this. Because a lot of times what will happen is the College Board is going to come out and they say, let some function f prime of x, or let some function be differentiable. Let me write it. It'd probably go easier. You'll get something that looks like this. They'll say, let f of x be differentiable from, and they'll give you some domain, A to B, whatever, it doesn't matter. Doesn't matter. And then they're going to go on and tell you a whole bunch of other things. Well, the very first thing you're going to do before you even start to solve the problem, as soon as you see that it's differentiable, you're going to say, all right, since f of x is differentiable from A to B, then f of x is continuous from A to B. And I should have not used brackets there. It will never be differentiable, or on a closed domain. It's always differentiable on an open domain. And that gets to the idea of one-sided limits, but we're not going to necessarily get into that right now. Or as far as the idea of open and closed intervals, yeah. If you do put a closed interval instead of open, the College Board doesn't dock you for it. I would, but they won't. Anyways, so if they ever say a function is differentiable, you're going to say, great, since it's differentiable, that means it's continuous. But you need to understand something. If a function is continuous, it doesn't mean that it's differentiable. If a function is continuous, it doesn't mean that it's differentiable. The converse of this statement is not true. If it's differentiable, then it's continuous. Splendid. But if it's continuous, does not mean that it is differentiable. So say I give you an equation. We'll let this equation right here, we'll let it be f of x. So this is going to be the equation f of x equals the absolute value of x. Well, friends, if I wanted to, I could write this absolute value equation, I could write it as a piecewise. I could write it as the negative portion of the graph. And then I could write it as the positive portion of the graph. Okay. So right here at the point 0, 0, this is where the graph turns. So notice the graph has a positive, it's a continuous function, it's an absolute value function. But remember that a derivative is a slope. It's instantaneous rate of change. Well, if it's a linear function, it turns out that instantaneous rate of change is the average rate of change because the slope doesn't change on a line. The slope of this line would have been -1. The slope of this line would have been +1. So if I wanted to actually write the equation of the derivative of the slope on the first would have been -1. The derivative of the second part would have been +1. But what would have been the derivative when it was at 0? Let's draw that. What would have been the derivative when it's at 0? Now notice, one of our old favorite functions that popped up. this weird step function, turns out it's actually the graph of the derivative of an absolute value. Notice the two one-sided limits, they don't equal each other. The limit for the derivatives, if I were to take this derivative function, if we were to look at the one-sided limits, notice the two one-sided limits, they don't agree. They're not the same. Just because the graph was continuous at 0 didn't mean that the derivative existed at 0. This kind of point, it actually has a special name. Call it a cusp. There it is. Call it a cusp. It's a point where f of x is continuous, but f of x is not differentiable. That's a cusp. So sometimes you guys maybe learn that an absolute value, you called this a vertex. Well, technically, it's not called a vertex, it's called a cusp. Biggest thing to remember is, hey, just because a function is continuous at a point doesn't make it differentiable. However, if a function is differentiable at a point, it's continuous. In other words, if this was my derivative, if my derivative was an absolute value function, we want that right there. There we are. If my derivative was an absolute value function, like this, not f of x, but if f prime of x was an absolute value function, I would have been able to say, okay, well, f of x is continuous. If the derivative exists, then it's continuous. But just because it's continuous does not make a derivative exist. Got to know which direction we can go. All right, gang, like I said, that was probably the longest we'll have of the entire year, at least for a long time, at least. So that was a lot. We covered a lot, but I think you guys can handle it because it builds off what we did for limits. So good. We'll see you guys in the morning. All right, have a great night. Talk to you later.